In this video, I'll discuss horizontal pressure gradients. And our starting point is the pressure that we derive from the hydrostatic balance. Here, pressure at some level z equals the pressure at the surface, that's atmospheric pressure, plus g, which is gravitational acceleration, times rho naught, our reference density, times the quantity eta minus z. And this is the thickness of the water column, or the height of the water column above the z, all the way up to the surface. Plus that last term, g, gravitational acceleration again, times the integral of rho prime, has all the density variations. And here's a sketch of the coordinate system. There's z pointed upwards from the undisturbed surface. The actual surface is at eta. It can be above or below 0. And then the z level that we're looking at pressure for, that's the dotted line here with the z next to it. And then I have the equation rho, the density, equals rho naught, the reference density, plus rho prime, that has all of the variations around the reference density. At this point, we're talking about pressure varying with z, with the vertical position. But it can vary horizontally too, with the x and y. So I'm going to rewrite this equation, and I'm just going to put in where there's x and y variability. This second equation is the same as the first, but I've added in that pressure is a function of x, y, and z. The surface pressure is a function of x and y. And then eta, or surface elevation, is a function of x and y as well. And so is rho prime. The next step is to take partial derivatives. The first one with respect to x, and then the second one with respect to y. Here's dp dx. You can see we have a partial derivative of the surface pressure, one of the sea level, and one of the integral of rho prime. And in this equation, I didn't include the parentheses x, y, z, or the parentheses x, y, because we already know what it's a function of. You can put that in, it just makes the equation look longer. And here's the partial derivative with respect to y. So the first term on the right-hand side, that's atmospheric. The second term has to do with sea level gradients, d eta dx or d eta dy. We call that barotropic. The third term has to do with variations. We call that baroclinic. The baro part of each of those refers to pressure. What I'd like to do is write horizontal pressure gradient. For that, I'm going to use this symbol. We can put an arrow over top. Now I have a symbol for the horizontal pressure gradient. And I can substitute in the terms for dp dx and the terms for dp dy and write this out long ways. Or I can recognize that, well, we have the horizontal gradient of pressure. The first term is going to give us the horizontal gradient of surface pressure. The second term is proportional to the horizontal gradient of sea level. And the third term is proportional to the horizontal gradient of the integrated density variations. So I can write that as this. And now we have all the terms. That's the atmospheric pressure gradient. And we can evaluate that with meteorological measurements. The second term is the barotropic pressure gradient. And we can evaluate that with measurements of the sea surface. The third term is the baroclinic pressure gradient. And we can evaluate that with density measurements. So what we did here is we started with an equation for pressure that came from the hydrostatic balance. And then we took the horizontal derivatives in both the x and y direction. And then we used this concept of a gradient that has both magnitude and direction, and combined dp dx and dp dy to give us the pressure gradient not only the pressure gradient, but its component terms from atmospheric, barotropic, and baroclinic pressure gradients.